Okay guys, in this video we're going to talk about Dalton's law of partial pressure, and we're going to roll for that. So here we go. So Dalton came up with this law that basically applied to what happens if you mix gases together. Okay, so through experimentation, what he basically was able to determine is that if you mix multiple gases together, oxygen, nitrogen, carbon dioxide, doesn't really matter what the gases were, but if you mix them all together, that there is no interaction between the gases. So if you want to find the pressure total of the system, you can just add up the pressure that each one contributes to that system. Okay. So this seems kind of simple, like, oh yeah, well for sure, you put a bunch of stuff together, you add them up, you get the total. But if you think about it, what he was really telling us is that gas 1 doesn't interfere with gas 2, and gas 2 doesn't interfere with gas 3. So you truly can add up the sums. Now this isn't always true for everything, because when you get into solution chemistry, we're going to find out that if you add two different liquids together, you don't get the total. So this is kind of works for gases, but it won't work for liquids later on in our unit. Okay. So if we take a look at Dalton's law and we actually kind of apply this idea of total pressure of our system, we can look at a couple of different ways that we apply this. Okay, so one way that you'll run into, and if you have anatomy physiology next year as a class you guys are taking, you'll run into this issue actually next year, or if you do anything in terms of biology in the future. So this graph right here, if we take a look, our y-axis is percent of oxygen saturation of hemoglobin. Okay, so we're talking about hemoglobin, basically what carries oxygen to our cells. The x-axis is your partial pressure of oxygen in millimeters of mercury. Okay, so at your lungs, at the place that you get the most oxygen in our bodies, we get a partial pressure of about 100 millimeters of mercury. Okay. This is the actual maximum amount of basically partial pressure of oxygen that we can get in our bodies, is at our lungs, because that's what we're breathing in, that's where we're actually absorbing that oxygen. Okay. Now, at your tissue, we get a partial pressure of about 40 millimeters of mercury. So we drop from about 100 millimeters of mercury down to 40. We lose about 60 millimeters of mercury of pressure of oxygen from these two different locations. Now, what that does to the hemoglobin is kind of interesting. Hemoglobin actually changes shape. Actually, it changes its geometric shape at the lungs compared to being at the tissues. And that change in shape actually happens gradually over your differences in partial pressure. Okay? So what happens is as hemoglobin changes its shape, it actually goes from being a molecule that absorbs oxygen in the lungs to a molecule that releases oxygen at your tissues. Okay, and it has it primarily to do with the difference of partial pressure. Okay, so if your body was out of whack in terms of its partial pressures, it would change how hemoglobin transports that oxygen. Now, if the tissue you only have 40 millimeters of mercury here, the reason why it drops is because at your tissue there's more carbon dioxide. So if you actually were to look at, well, what is taking up this partial pressure, because you still need 100% somehow. So the difference there is that at your lungs you have very low carbon dioxide, and at your tissue you have really high, much higher carbon dioxide. So the hemoglobin sees the difference there, it feels that difference in partial pressure, it changes geometry, which allows it then to dump that oxygen into the tissue or into your cells, so then your body can use them. Okay, so it's one way that we kind of can use partial pressure and how it applies to things that we use in our system. Now, if you notice, you can actually track the volume of oxygen that gets dumped also by this graph, but that's a little bit more of a topic for anatomy physiology if you get into that world. Okay, if you take a look at Dalton's law in terms of just some cylinders and pressures, again, we have in this case, we have hydrogen gas, partial pressure of hydrogen gas, 2.4 atmospheres, and we have a half a mole of hydrogen gas inside of here. If we go over here to helium, and we have 6 atmospheres of helium pressure, and we have 1.25 moles of helium here. Okay, so if we take this gas and put the two together, okay, so the 1.25 moles of helium and the 0.5 moles of hydrogen gas, we're going to get 1.75 moles of gas total there. Okay, which will give us a total pressure of 8.5 or 8.4 atmospheres. We're just adding the two things up. Okay, so again, notice how we're keeping these the same, half liter at 20 degrees Celsius for every case, because if we change volume and change temperature, obviously that's going to affect our results. Okay, so this is kind of another visual effect of how Dalton's law works. We're going to dive down here to this practice problem. This is different than what is on some of the older documents, so this is a new practice problem for us to work our way through. Okay, so let's take a look at this practice problem. Mixtures of helium and oxygen gas are used in deep sea scuba diving. Okay, so if you go normal scuba diving, they just use air. But when you go deep sea diving, where they actually go down into depths, I believe, below like 100 meters or so, that kind of stuff, they get down really deep. They need to use helium and oxygen, so that actually stops this thing called a bends. Okay, it's basically a place where nitrogen bubbles out of your blood when you come back up, which is dangerous. So for a particular dive, they make this kind of mixture. You have 46 liters of helium at 20 degrees Celsius and 1 atmosphere pressure, and 12 liters of oxygen at 20 degrees Celsius and 1 atmosphere pressure. Okay, so same pressures, same temperatures, but you're putting more helium in and less oxygen in. Okay. Now, when they do that, they actually pump those into their scuba tanks, and the tank has a volume of about 5 liters. Okay, so we have a 5-liter tank. Okay, and what we want to do is solve for a couple of things. What's the partial pressure of each gas, and then what's the total pressure in the tank at 20 degrees Celsius? Okay, so we're going to keep our temperature the same throughout this whole thing. Okay, so let's break this problem down and then solve it. Okay, so we're going to use a little bit of our gas laws and then now adding Dalton's law to solve this problem. Okay, so I'll pause it here, let you guys get a chance to work on that, and then we'll work it out. Okay, so we're going to start with helium here, and then we're going to work our way down to oxygen for this problem. Now, because of Dalton's law, we know that each gas is going to contribute their own amount, and then we can just add them up. Okay, so we started with helium having a 46 liters of it, and we were at 1 atmosphere pressure. Well, we converted that down to only compressing it into 5 liters of space. So we want to solve for what is the new pressure. Okay, so 46 times 1 divided by 5. So we take this and we divide this by 5, and we get a new pressure of 9.2, right? 9.2. So we have 9.2 atmospheres. This is for helium. Okay. Now, do the same thing for oxygen, where we had 12 liters at 1 atmosphere. And we went down to 5 liters. So what is the new pressure for the oxygen? So we take the 12 divided by 5. And 12 divided by 5 is 2.4 atmospheres for the oxygen. Okay? So we know that the partial pressure of helium is 9.2. The partial pressure of oxygen is 2.4. So then if we add those two up, so we take 9.2 plus 2.4, and we get total pressure of 11.6 atmospheres here. Okay? So again, we're applying Dalton's law here, saying that those two things work independently, but we're also applying Boyle's law to do some of the math inside of here. Okay? All right, so that is Dalton's law of partial pressure. In our next video segment, we will go into diffusion and talk about how diffusion works.